Suppose we have a bacteria colony that started with 200 cells at hour 0 and is doubling each hour. Well, this graph shows us more or less what will happen from hour to hour. So at 0 hours we have 200. At 1 hour we have 400. At 2 hours we have 800, and then we're off the chart. But what this suggests is that from 0 to 1 hour it stays at 200. From 1 to 2 it stays at 400. Well, we know that that's not what happens in reality because we know that it's much more of a continuous growth situation. With this idea that it's doubling every hour, so if we just step up here, after 1 hour we're at 200 times 2 to the first, then 200 times 2 to the second, 200 times 2 to the third, because every hour we're doubling, and the exponent here is counting the number of hours. So every time we step up 1 in the exponent, we double. The ratio from hour to hour is 2 to the first, or 2. Well, what if we decided, let's see what it looks like every half hour instead of every hour? Well, what we can do is we can set this interval. So now it's measuring every half hour, and you can see that suddenly we have twice as many bars. And the ratio now, going from half hour to half hour, is no longer doubling. It's increasing by 2 to the 0.5 because half hour is equal to 0.5 hours. And that's 2 to the 0.5 power, which is the square root of 2, which is about 1.4142. Now as we step up, we can see we're no longer doubling with each step. It's taking us 2 steps to double. Each step we're increasing by this factor of the square root of 2, or 1.4142. And so this is a better representation of what actually is happening with the bacteria. Although again, it's not as if they grow, then half an hour later grow again. So let's try the next interval, 15 minutes. Again, twice as many bars. And now our ratio is not 2 to the 0.5, but 2 to the 0.25, because 15 minutes is equal to 0.25 hours. The exponent, again, is counting the number of hours that have passed since 0 hour. So as we step up now, our ratio is equal to not the square root of 2, but the fourth root of 2, 2 to the 0.25, which is approximately equal to 1.189. So now as we go up, we're going up with each step much less rapidly, because each step represents only 15 minutes worth of growth rather than 60 minutes worth of growth. Well, let's change it again. Now we're at 5 minutes. And so our ratio now is 2 to the 0.0833, which is 2 to the 1/12, because there are 12 5-minute intervals in 60 minutes, so a 5-minute interval is 1/12 of an hour. So now we're increasing by a ratio of 1.0595 per time period, but each time period is only 5 minutes. If you look at our histogram, we have so many bars that it's starting to look almost like a solid continuous figure with a smooth curve. Well, let's go one step further. Let's get to every minute. So now we're going up by a ratio of 2 to the 1/60th power, because whenever we increase the exponent, we're increasing it by 1/60th, because that's what a minute represents, 1/60th of an hour. So each minute now we're saying that the number of bacteria increases by a factor of 1.0116. In other words, each minute there are 1.0116 times as many bacteria as there were the previous minute. So now as we step through, we can see the growth is much, much more gradual. It takes us a number of steps just to get even to 300, and so we haven't even doubled yet. It's going to take us a full 60 steps until we get to 400, because again, that represents 1 hour. Each step represents 1 minute. Now let's fit a curve to it. You can see here that this red curve now fits very smoothly along the edge of our histogram, whereas when the interval was much bigger, it touched all the corners, but it was not necessarily a very smooth fit.